It works. Next, previous. Good.
Hi, I'm Ulises Torrella. I'm a PhD student at the Western Norway University of Applied Sciences. And with my supervisor, Violet Kaipun, we work on concurrent system and mainly in active objects. And this is work in collaboration with Francesco Dagnino and Paola Giannini to make these systems resource aware and to verify the proper use of resources statically. So let's start by what are these resource aware active objects and what's our goal in general. So we work on a field that is workflow modeling, that is very abstract concurrent systems where we have many processes that have shared resources, and these resources have a limited availability. That means copies that can be linear or fine bounded, or that also means that they can be accessed but in a certain way. Maybe they're private, public, or they have to be accessed by a certain kind of user. And what we want, our goal is to provide a framework to model these systems and to guarantee that the use is resource safe, so that the resources are being used correctly. So when I talk about active objects, I'm just talking about the object-oriented flavor of actors. So think about actors in distributed computing entities that communicate via message passing. And in our specific case, where we have a scheme that is called a cooperative scheduling scheme that allows for actors to handle more than one message at a time, but they don't have full concurrency. They receive a message and execute and process it until completion or until a blocking statement that is considered an explicit yielding of control, and then they can pick up another thread and continue processing another message. So that gives us actors that will have that will have many threads, of which only one will be running and the rest will be suspended, but all the threads will have access to a common resource pool. To access this resource pool, I already spoiled it. A thread performs a hold that asks to move a resource from the resource pool into its local environment. And if it has a resource in the thread's local environment, we can release it into the actor's pool thread to be accessed by other threads. So resources are not visible for other actors. They can only be passed around via message passing. So we have future-based communication, and the messages just say, and I said before, this is an object-oriented approach. So sending a message is actually performing a method call and saying, I want in future F the result of A performing M with the values, the resources that I passed. And then the awaiting statement will be synchronizing on this future. So how do we model this hold and release? And how do we make it resource aware? We use something that is called grades. That is probably, people know it here, but there's just annotations that we use on our syntax and on our type system that tells us how we are using this resource. For example, we can say that a type is graded. That means that this element can be used in this mode. We can grade a variable, and we can hold a resource in a certain mode. And this the meaning of this grade is given by some mathematical structure, usually some kind of order semi-rings that will tell us if it's a quantitative mode of use. So it can be linear, it can be affine bounded, or qualitative, private, public, or this kind of other modes of use. In our system, we follow the kind of normal trend of using commutative monoids, but we add one extra operator to make a resource consumption deterministic, because usually in literature, resource consumption is non-deterministic. And so the normal thing is to have grades in a set G, a partial order in between them, addition operator, a binary addition operator, a neutral element for that operator, and a lower that is also the lower bound for the order. And we include the extra partial function that is the subtraction that models the residual element of taking a grade G from a grade H. And it's partial because you cannot consume from any kind of grade H. So for example, if we want to model linearity, we can just define 0, 1, and infinity as our weights. We can say that 0 and 1 are less than or equal than infinity, and then 0 will be the neutral element of the addition. Infinity will be the absorbing element of the addition. 1 plus 1 if it's linear, so if you use it more than once, you need to have it unbounded, an unbounded amount of copies. And for the subtraction, we just have to say that 1 minus 1 is 0. And if I take 0 from anything, I just have what I have, and anything from infinity will have infinity. And for the other kind of qualitative modalities, it's even easier. We just define a joint semilattice and use the junction as the addition operator, and then define the subtraction as just if just when they are comparable, and we take the biggest one. So going back to the language, the characteristic that we have in them is going to be, we're going to define actors that have a list of graded resources that can be accessed by the running threads. We will have future-based communication in which futures will be first class, but because futures can be holding graded resources, if we were to grab a future, pass it, and read it twice, we could be violating the grade of the resource inside. If we had it linearly, we can read it twice. So the solution we implemented for in this case is just make futures linear. You can pass it around to delegate task, but you can only read it once. We also have non-deterministical branching and recursion to model looping behaviors. So going into the semantics, we define a tree-level semantics. The first one is just value expressions, very simple, not going to go into that. And the expression level is the one that is executed by actors. So an actor can send a message, await for a future, hold a resource, release a resource, sequentially compose, and non-deterministically branch. The most important thing about this semantic step is that it's going to be a label transition in which we label if what is written and read from the outside system, and that is seen from the process level. The process level models the system as a whole, where we have the running threads and the suspended threads differentiated by the full and empty dot that is being run by an actor, executing an expression E in a lambda environment and promising to fulfill a future F. Actors can be idle, and they can be with messages that can be a future being resolved with a value or a future being spawned to fulfill a method code. We parallelly compose these processes to build our system, and then we have a state that is phi that maps actors to resources. And once we have a state and parallel composition of processes, we can define our semantic. So I can imagine if you see this parallel composition, you think is probably commutative, but sadly no, because this is what we use to ensure that we don't have circular dependencies of futures. We define a precongruence in which we can swap two processes in the parallel composition only if Fp, that is the futures produced by P, and the intersection with the futures read by Q is empty, and similarly the opposite way. So then we generate a way of producing futures to the right and reading to the left, and avoid a circular dependencies on futures. And what I said before of this converging scheduling is modeled here by allowing to start with a precongruence to a suspended thread, and only we can go idle if the expression is trying to perform a reading of a future that is an await, and this is the only way we can yield control. So I'm just going to show the most important semantic rule, that is the one where resources are consumed. And it basically tells us that if an actor is trying to execute a thread that will try to hold a resource in mode G, it will have to modify the state. We update the thread and modify the state with the residual H minus G that can be undefined because it's a partial function. And if it's undefined, our computation is stuck. And we don't want to have a stuck computation, and then therefore we implement a type system to verify that that won't happen and our system will be well behaved. So our type system is very simple. We have three types of contexts: a standard typing context of variable to types, a linear context sigma for the futures, because we said futures are linear, so we have to verify that are being used linearly, and the same kind of actor environment that we have before, mapping actors to resources to track what resources are needed for expressions. We have three types: the unit type, graded resources, and the future type that promises to resolve into a type T. Can be a unit, can be a resource, or can be another future, and it's also annotated, and this is a weird thing with our system, that is annotated with an actor environment, because futures are the only way we have to synchronize our processes. And when we synchronize processes, we not only get the result of the execution, we also get the information of the side effects that this execution had. So now we know that when we synchronize, we get a value of this type, and we also get information of which resources have been released to the system and are now available for us, and we can include them into our context to continue execution. To do that, we type expressions with a left-hand actor context that tells us what resources will E require from the actors. It will resort to a type T, and what resources E will release into the context. The full typing context for expressions will also have the futures that it will consume, the variables that we'll use, and it will be annotated with the actor that is executing the expression, because the expressions can be a hold and release that is dependent on the actor. The typing judgment for processes will also require a certain amount of resources to be placed in some actors, and will require to read some futures to the left, but because it's a process, it will also be producing futures to the right, and then we can verify this chaining of futures read to the left and produced to the right when we compose them together. One more thing, we have one extra notation, because we show you now that we want to show note per termination. We annotate expressions and processes with the amount of possible steps towards a possible termination. So return will be annotated with a 0, and then we start adding up internal expressions. And when we have an undetermined cycle choice, we pick the measurement that is the smallest. And we define a terminated configuration as the one that is only idle actors and resolve messages. So let's see the two most important rules, typing rules, that are also the ugliest. So bear with me. I put some colors to try to explain them. For expressions, the most important one is the composition, the sequential composition of expressions. So we will need to split the actor context and also the future context, but most importantly, the actor context. We will need to split it in two, in one for E1 and one for E2, but also resources released by E1 should be available for E2. So we have to also split the right-hand context, the effect context of E1 to be passed for E2, and the other part to be propagated. For the parallel composition of processes, we have a similar kind of problem, that we have futures that can be needed, produced by P and required by Q. So we do similarly the easy way for the actor context, and for the futures, for the future context, we pass one to P, one for Q, and we take one piece, we split the produced futures in two. One goes to Q, and the other one is propagated outside, and we need to add some other checks, as for example, checking that whatever is coming into E2 and coming propagated outside, so they're not matching, is also not breaking linearity. So let's move into soundness. There were some other details I want to get into in the mark contact and stuff, but the soundness of our system is that resources are used correctly, and that means that every time we reach a hold statement, it will be successful. And the strategy we use to prove that our system is sound is first to show subject reduction and the preservation of the futures that we require, or dependency on futures. And then we show that for every configuration that depends on no futures, there is a path towards termination. Once we have subject reduction and this weak termination, we can show that if we don't depend on any external futures, there, no matter what step we take, there will still be a path toward termination. That means that it cannot be stuck, and that means that it's resource safe, that we can never reach this state in which we cannot perform we cannot get the residual between two grades. It also tells us that it cannot be live logged and there cannot be orphan messages. So in conclusion, we introduce an active object language for workflow modeling with a parameterized notion of resource awareness. We implemented a type system that guarantees that all model workflows in our framework are resource safe. And as for future work, we are working on making the system fully object-oriented because we cannot cheat it in the current version, and we just instantiated all the objects. The overall goal is to make it object-oriented, but now we're just working on the instantiation of the objects, and they can just easily communicate. And now we're working on being able to instantiate objects within an object, and that has certain complications, as you can imagine. And the other thing that is almost done, but it's including grades and futures, because the use of linear futures is just an overkill to cater for the case of quantitative grades. So we don't want to copy things that we have a certain amount of copies, but it doesn't mean anything for the cases of other kind of modalities. So we are working on that. And that's it for me.